Hey, welcome back. Today we're diving into something that quietly powers the entire internet, and most people have never even heard of it. We're talking about Unicast and Anycast, two ways data travels across networks, but they work in completely different ways. By the end of this video, you'll understand why one of them makes the internet faster, safer, and more reliable. Let's get into it. Alright, let's start with Unicast. And honestly, this is how most internet traffic works today. Unicast simply means one sender, one receiver. When you send an email, watch a YouTube video, or load a web page, that's Unicast. Your device sends a request, and one specific server sends the data back directly to you. It's like calling a friend on the phone. You dial their number, and you two are connected. Simple, right? So here's what Unicast looks like in real life. You type a URL in your browser, your computer sends a request to one specific IP address, the web server. That server sends the web page back to your IP address and only yours. Every single packet has a unique destination. It goes to exactly one place. This works great, but what happens when millions of people all want to reach that same server at the same time? That's where things get interesting. Here's the problem with Unicast at massive scale. Imagine you have one server in New York, and suddenly a million users from Tokyo, London, Sydney, and Sao Paulo all want to access it. Every single request travels all the way to New York. That's huge latency for users on the other side of the planet. Plus, that one server has to handle everything. If it goes down, everyone's affected. You have a single point of failure. Not great. This is where Anycast comes in, and it's genuinely clever. With Anycast, multiple servers in different locations around the world all share the same IP address. When your request goes out, the network automatically routes you to the nearest or best performing server. You don't choose it. The routing protocol figures it out for you. Same destination address, but you land at the closest node. Super elegant. So how does Anycast actually work under the hood? It uses BGP, the Border Gateway Protocol, which is the system that controls routing on the internet. Each Anycast server announces itself as a destination for the same IP address. BGP routers look at the network path and pick the one with the fewest hops or best performance. It's like GPS for your data. It finds the fastest route automatically. No manual configuration needed on your end. Let's compare them side by side. With Unicast, one unique IP, one specific server, traffic goes to that exact machine. With Anycast, one IP shared across many servers globally, traffic goes to the nearest one. For Unicast, if the server fails, users are down. For Anycast, if one node fails, traffic automatically reroutes to the next nearest server. Unicast is point-to-point. Anycast is intelligent, distributed, and resilient. One of the most common places you see Anycast in the real world is DNS. Remember Cloudflare's 1.1.1.1 or Google's 8.8.8.8? Those are Anycast addresses. Cloudflare doesn't have one server at 1.1.1.1. They have hundreds of servers and data centers around the world, all announcing that same IP. When you query 1.1.1.1, you hit your nearest Cloudflare node, not some server halfway around the world. That's why DNS resolution feels almost instant. Anycast is also the backbone of content delivery networks, CDNs. Services like Cloudflare, Akamai, and Fastly use Anycast to serve content from edge servers closest to you. When you stream a video or load a website, you're not connecting to the origin server. You're hitting a nearby edge node. This massively reduces latency and distributes the load across hundreds of locations. That's why YouTube doesn't buffer even during peak hours. Here's another superpower of Anycast: DDoS mitigation. In a distributed denial of service attack, attackers flood a target IP with massive amounts of traffic. With Unicast, all that traffic hits one server and takes it down. But with Anycast, that flood of attack traffic gets spread across all your nodes globally.
Each server only absorbs a fraction of the attack. One node might get overwhelmed, but the rest keep running. It's like routing a flood through multiple channels instead of one.
Now, let's be fair. Unicast isn't going away, and for good reason. Unicast is stateful. It maintains a session between you and one server. That's essential for things like video calls, file uploads, banking sessions, and anything that requires continuous back-and-forth communication. When you're uploading a file, you need that same server to receive all the pieces in order. Anycast can't easily maintain that kind of persistent session. Each protocol has its place.
Anycast does have limitations worth knowing. TCP connections are stateful. They need all packets to arrive at the same server. With Anycast, if network conditions change mid-session, packets could be routed to a different node, breaking the TCP connection. This is why Anycast is most commonly used for UDP-based services like DNS, or for the initial connection layer, not for long-lived TCP sessions. Engineers design around this carefully. It's not a deal breaker, but it's a real constraint.
While we're here, let's zoom out. There are actually 4 types of IP communication. Unicast, one-to-one, broadcast, one to all devices on a network, multicast, one to a selected group, and Anycast, one to the nearest in a group. Each one serves a different purpose. Broadcast is used internally on local networks. Multicast is used for live streaming to groups, and Anycast powers the global internet speed and reliability. Together, they cover every communication pattern you need. Here's something interesting. Anycast works in both IPv4 and IPv6, but IPv6 has native built-in Anycast support. In IPv4, Anycast is kind of hacked together using BGP routing tricks. In IPv6, Anycast is a formally defined address type alongside Unicast and multicast. IPv6 Anycast addresses are allocated from regular Unicast space, but they're assigned to multiple interfaces, and the network delivers packets to the nearest one. It's cleaner, more standardized, and increasingly important as IPv6 adoption grows. Let's talk about who actually uses Anycast at scale. Cloudflare's entire network runs on Anycast. Their DNS, their CDN, their DDoS protection. Google uses Anycast for 8.8.8.8 and their global load balancing. AWS uses Anycast for global accelerator, routing users to the nearest AWS edge location. Akamai and Fastly power most of the world's biggest websites using Anycast CDNs. These aren't small deployments. We're talking about hundreds of data centers, millions of requests per second, all handled through smart Anycast routing. One of Anycast's best features is automatic failover. If one of your Anycast nodes goes offline, BGP routing protocols detect that the node is no longer announcing that IP address. Within seconds, traffic that was heading to that node gets rerouted to the next nearest available server, automatically, with no manual intervention. For Unicast, this requires complex health checks, load balancers, and failover logic. With Anycast, the routing infrastructure handles it for you. Its resilience baked into the network itself. Let's talk numbers. Imagine a user in Tokyo connecting to a Unicast server in New York. They're looking at 150 to 200 milliseconds of latency just from the physical distance. Light takes about 65 milliseconds to cross the Pacific, and actual network routing adds even more. Now, with Anycast and a node in Tokyo, you're down to single-digit milliseconds. For DNS lookups that happen hundreds of times per page load, this adds up massively. Anycast is one of the biggest reasons the modern web feels as fast as it does.
So if you ever want to set up Anycast yourself, here's the key concept. BGP, or Border Gateway Protocol. It's what allows multiple servers to advertise the same IP prefix. You need to own an IP block, set up BGP sessions with upstream providers at each location, and each location announces the same prefix. Routers on the internet then pick the best path to that prefix based on hop count and routing metrics. It sounds complex, but cloud providers like AWS, Cloudflare, and Google Cloud abstract all of this away with services like Global Accelerator or Anycast Load Balancing.
Quick recap before we wrap up. Unicast, one sender, one specific receiver, unique IP. Great for stateful connections like HTTPS and video calls. Anycast, one IP shared across many servers globally, traffic routed to the nearest node, automatic failover, lower latency, used for DNS, CDNs, and DDoS protection. The internet uses both, Unicast for most application traffic and Anycast for the critical infrastructure that makes it fast and resilient.
And that's Unicast versus Anycast. Every time you do a DNS lookup, load a CDN asset, or stay protected from a DDoS attack, Anycast is quietly working behind the scenes. It's one of those technologies that most users never think about, but without it, the internet as we know it would be much slower and far less reliable. If you found this helpful, give it a thumbs up and subscribe for more networking deep dives. I'll catch you in the next one.